Hello students, this is Revathi, Assistant Professor, Department of Electrical and Electronics Engineering, KPR Institute of Engineering and Technology, Coimbatore. I am going to present a topic on JK flip-flop. So we have studied three types of flip-flops earlier. So today we are going to see about JK flip-flop. So JK flip-flop is a type of flip-flop. So it comes under sequential circuits. So this was invented by the scientist Jack Kilby. So that's why it is called JK flip-flop. So due to the undefined state in the SR flip-flops, another flip-flop is required in it, that is the JK flip-flop. It is an improvement on the SR flip-flop. S is equal to or is equal to 1 is not a problem. Here there are two inputs J and K, and similarly there are two outputs Q and Q bar. Q is the normal output and Q bar is the complementary output. If Q is 0, obviously Q bar is equal to 1. If Q bar is equal to 1, Q bar is 0. So here, this is realized using SR flip-flop. So this is SR flip-flops, so which has a NAND cross-coupled logic. Here, S is given the input J and Q bar. J input and Q bar input are ANDed together and it is given as S input. Similarly, J and Q are ANDed together and it is given as R input. Since it is a flip-flop, it is an edge-triggered device, so therefore the clock pulse is given at the positive edge. So this is clocked JK flip-flop. Here the SR flip-flop is realized by using only NAND gates. So this is the positive edge detector circuit. So the input condition of J equal to 1, K equal to 1 gives an output inverting the output state. So we are going to see the truth table of clocked JK flip-flop. So here there are four cases. One is J equal to K equal to 0. Next one J equal to 0, K equal to 1. Next case J equal to 1, K equal to 0. Then the last case J equal to K equal to 1. So in simpler, if both the inputs are 0, what happens to the output? If both the inputs are given as 1, what about the output? If any one of the input is high, what about the output state? So let us see one by one. The first case, when both the inputs are given 0, that is J equal to K equal to 0. So when both the inputs are 0, S equal to 0, R is equal to 0. So according to the truth table of SR flip-flop, there is no change in the output. So therefore output does not change. So the output follows the previous state. Second case, when J equal to 1 and K equal to 0. Here there are two possibilities. When Q equal to 0, what happens? And if Q equal to 1, what happens? So if Q equal to 0, similarly Q bar is equal to 1. When J equal to 1, K equal to 0 and Q equal to 0, S equal to 1 and R is equal to 0. So according to this, the output is set state. That is, the output will be 1. In the second possibility, if Q equal to 1, Q bar is equal to 0, that is when J equal to 1, K equal to 0, Q equal to 1, S is equal to 0, R is equal to 0. If S and R are given low, there is no change in the output. Therefore, when the inputs J equal to 1, K equal to 0, it makes Q equal to 1. That is set state. Third case, when J equal to 0 and K equal to 1. Here also there are two possibilities. When Q equal to 0 and Q equal to 1. Here, as seen earlier, when j equal to 0 and k equal to 1, it makes q equal to 0. That is reset state. When both the inputs are given high, here also there are two possibilities. Q equal to 0 and Q equal to 1. When j equal to k equal to 1, the output gets toggled. This is said to be raise around condition in JK flip-flop. So this is the characteristics or truth table of JK flip-flop. So it is given three inputs. That is Qn is said to be present state, J is one input and K is another input. Qn plus 1 is the next state. So here when j equal to k 0, k equal to 0, if Qn is equal to 0, so if both the inputs are given 0, the next state follows the present state. So therefore it follows the present state, that is 0. When j equal to 0, k equal to 1, so that is reset condition, therefore the output is 0. When j equal to 1, k equal to 0, set output is set, that is 1. When both the inputs are 1, it gets toggled, so therefore Qn is 0, so it gets toggled, that is Qn plus 1 is equal to 1. Similarly, if both the inputs are given 0, there is no change in the output, so it follows the previous state output. So therefore Qn is equal to 1 and Qn plus 1 is equal to 1. There is no change in the output. When j equal to 0, k equal to 1, irrespective of the present state, the output is reset, that is 0. When j equal to 1, k equal to 0, the output is set, so therefore q equal to 1. Where both the inputs are high, the output gets toggled, so therefore present state is 1, so therefore the next state is gets toggled, therefore it is 0. So it is given like this. When j equal to 0, k equal to 0, so the present state is Qn. There is no change in the output. And if it is 0 and 1, so the output is reset, so therefore 0. If it is 1, 0, the output is set, so therefore Qn plus 1 is equal to 1. When both inputs are given high, the output gets toggled, so therefore Qn bar. So if we plot a characteristic equation using K-map with these inputs Qn, J and K, so we will get this characteristic equation as JQ bar plus K bar Qn. So this is the next state equation or characteristic equation of JK flip-flop. So this is the timing diagram. So the pictorial representation of the truth table is the timing diagram. Here the clock pulse is given, so it is triggered at the positive edge since it is a flip-flop. So this is the uh, J input and this is the K input. So this is the Q output. If J equal to 0, K equal to 1, the output is reset. So therefore it is 0. When both the inputs are 1, the output gets toggled. So therefore Qn is 0 in the previous state. So therefore it gets toggled, that is it is changed to 1. If both the inputs are 0, there is no change in the output. So it follows the previous state. The previous state output is 1. So therefore it follows the same. If j equal to 1, k equal to 0, the output is set, that is q equal to 1. So therefore q equal to 1 till the next positive edge. So here when j equal to k equal to 1, the output gets toggled. So the previous state is 1. So therefore it is toggled to 0. Again at the next in a positive edge, where both the inputs are high, the output gets toggled. So therefore the previous output is 0. So it is toggled to 1. So this is the timing diagram of JK flip-flop. So next, raise around condition. So what do you mean by raise around condition? As we discussed earlier, when j equal to k equal to 1, so the output gets toggled. So that is the condition is said to be raise around condition. So this raise around condition can be avoided by using edge triggering JK flip-flop. using master-slave configuration. So this is the JK flip-flop using only NOR gates. So this is similar case as we have seen in the last slide. So that is JK flip-flop using NAND gates. Here instead of NAND gates, here it is used in NOR gates. That's it. So this is the master-slave configuration. So there are two flip-flops. One flip-flop will act as master and the other flip-flop will act as slave. So this portion is nothing but this portion and this portion is nothing but this portion. So we have seen already. So this is the master flip-flop. This is the slave flip-flop. So here the clock pulse is given simultaneously. So that is clock pulse is given at the positive edge in the master's flip-flop. Clock is bubbled, that is inverted, and is given as clock pulse to the slave flip-flop. If it is triggered at the positive edge, slave will be triggered at the negative edge. Then one more difference is the output of the master flip-flop is given as input to the slave flip-flop. So once the master is triggered, so after we are getting the output, the slave will be triggered. So this slave will obey the master flip-flop. So that's why it is called as master-slave configuration. So as we discussed earlier, the race around condition will be avoided using master-slave configuration. Thank you.